this was for me. Oh,
That's
look
for
at
you.
damn, that looks good.
Thanks. I really I don't know, some sort of possession took over me and I actually understood what I was writing.
You will not be getting something like that from me.
I'm gonna be so real.
Yeah, I don't even
my
have the
logic and
last one
pursuits
graded
made it
yet,
clutch.
so
I
is
look
that,
back
should I
and
wait till
look
Friday or?
Yeah, I mean, I have everything done, it just like looks ugly.
It's, make it pretty, I like that.
I was
That
gonna
looks
say,
great.
mine is all on here, so.
I'll try
Oh.
my best to make mine read.
Okay, Friday's great, Friday's great. You don't ever have to turn in anything
I
anymore.
just
You're
scribbled
good.
Automatic
A's.
And I got you.
Hey, now we know, like, we got it over with in the start of the semester, no one can do that plan.
Oh, folks. It's a pretty great story though, literally the first time. As long as you're cool with it, you know, as long as we're cool, everything's good.
At least he was there too,
Kind of.
like, caught his plan.
That was
No.
That was planned.
Otherwise, I feel like you would have came in here and be like, have you seen my plan? And you just go, oh.
Oh.
It just left.
Word.
Your legs and walk away.
Oh my gosh.
Gaslight on what plans? There's never been a plan.
What's a plan? 2 years.
It certainly didn't have a white pot in leaves, did it?
No.
Oh, next Wednesday.
No, really?
Oh, now, come on.
No, I have a quiz in my first
No,
class.
this is like. I knew you were gonna say that. I kinda did when I thought this, I made it up, I was like, Sophie's gonna have something on that.
I do, I hate to say.
But you have something every day.
I do, I really
So, so on in-world class, there's just this is definitions.
Oh.
Okay, it's closed note, but it's like, what is an equivalence relation? What is the integers mod? Just define those things. And then the thing we're gonna talk about today, what is a group? Which is literally the fundamental thing for the rest of the freaking semester. Group. So it just, so if you look on the announcement for this, it's got the exact definitions you need to know. And so if you can find those, right? Okay, sweet.
We got over it.
We're all good on that stuff. Fantastic. Cool. So let's just do a quick, like, together summary of something and then push it further. What is that? Did we talk about that? I think we did, but we had a 3 here.
Integers?
Yes, integers what? Integers mod n. So this is the integers modulo n. And what that means is that we've set up an equivalence relation on the integers. So 2 integers, a and b, are equivalent if and only if n divides their difference. And let's translate that. What does this mean? When you see this, it's going to be a thing that you'll get used to thinking about, because literally you're going to think about this almost continually in here, things dividing other things. But that means that b minus a, so i.e., b minus a is a multiple of n, an integer multiple of n. Does that all make sense? And then, in other words, b just differs from a by a multiple of n. So I like to write it like this. I like to, thinking about it in all these ways is important, and different times will call for different versions of this. But b and a differ by a multiple of n. And then what that does is it has the effect of tying together 0, n, 2n, 3n, minus n. So let me draw that instead of just saying it. It's going to make all these things the same. It's stitching together all these multiples of n, minus 2n. They're all the same. And then if I'm at 1, for example, that's the same as n plus 1. and minus n plus 1. And it's stitching together all of those things into equivalence classes, which we can think of like this. Z mod n is just these equivalence classes. So we get a partition of the space of integers into n distinct classes. And each of these classes, this is all the things that differ from 2 by a multiple of n. So what's in here? We've got 2 plus 0, 2 plus n, 2 plus 2n. On down the way is 2 minus, and you put plus or minus here to make that even more comprehensive. So remember that each of these are sets. Each of these things is an entire set, but we think about it as an entity, which is really cool and crazy. And I think that's kind of all I wanted to say about it, except I want to talk about operations in Z mod n. So we can define plus and times, this is my multiplication, looks like a little dot, on Z mod n as follows. So we're setting an algebraic structure up on these things. We say that a plus b, now watch how I write this. I'll just put a little mod n right here. You can just tack on a mod n at the end of an arithmetic operation to let the reader know the whole thing is in mod n space. But the way you would do this is you would take a mod n plus b mod n. And hell, you might have to mod that thing again. You just keep modding until you're back in this space here. So let me give you an example, because that might be a little big. Just judging by some facial expressions, I think maybe I should give an example. So e.g., if I'm in Z mod 5, and I said to you, let's take 3 plus 7 mod 5, then that's going to be 3 mod 5 plus 7 mod 5. What's 3 mod 5?
2, right?
No. But I know how you're thinking about it. I know what you're thinking.
Is it the other way?
Well, if you divide 3, so how many times does 5 go into 3? Let's think about it. You're thinking about it the right way with remainders.
0.
And then what's the remainder? So 5 goes, let's divide 5 into 3. So 3 equals 0 times 5 plus 3. That's your modulo there. You were thinking right, Sophie, about it being a remainder.
Yeah.
You were just doing it like, you wouldn't have to do that unless this number's bigger than your modulo. Then your method would work.
Okay.
Or 5 mod 3 would be 2. If they had them reversed, then you would definitely get the 2. What about 7 mod 5? What's that?
That one's 2.
That one's 2. So this is 3 plus 2 mod 5. And what is that? That is 5 mod 5. That could be my answer, but what's a prettier version? What's the remainder when I divide 5 by 5? 0. Did you say no? Okay. Okay, good. Because if you did, that would be everything Cormac says is right from here on.
And then you got the 3 plus 2 mod 5 by doing 7 mod 5 for 2, and then you just are modding 3 plus 2?
Yes.
Okay.
Yes, and we could do it up here too, so let's do it both ways. This is just 10 mod 5. And when I divide 10 by 5, the remainder is 0. I get the same answer. Sometimes, so like why am I doing this? Because sometimes it's easier to do it here, and sometimes it's easier to do it here. just know you can break it apart. We also have this, and here's where it really can pay off, that A times B mod n is equal to A mod n times B mod n. So, for example, if I were to do 3 times 7 mod 5, can we do that without, what is that? What should be the answer? 1, right? This is 21. 5 goes in evenly and they got a remainder of 1. So we know the answer is 1. So let's just check this. This is 3 mod 5, which is, we know 3. And then 7 mod 5, which is what? 2, because we already did, oh yeah, we already did that. So 3 times 2, and I keep my little modulo 5 out here, and that's 6 mod 5, which is 1, because that's the remainder after I divide 6 by 5. So it checks out both ways.
This is kind of a nitpicky thing. But
Yes, sir. Yeah,
when you
please.
say equals, you're talking about congruence, right? So you're talking about congruence.
Thank
of
you.
Set, right?
Yes.
Like an equivalence class?
Yes, you are correct. This should essentially be an equivalence, because we are talking about weird things that, yeah, thank you. That's not nitpicky, that's good shit. Yeah, because we are talking about sets of things. So here we use equivalence, the triple equality. Yes?
Is your notation up at the top there, you said it's A mod n plus B mod n?
Yes.
But then down there you did
You multiply.
A mod n times B mod
Well,
n?
so this is a new operation.
Oh, it's a new one, I'm
Yes,
sorry.
ma'am, yes. So this is how we do plus, this is how we do times.
Okay, sorry.
No, it's okay, thanks for asking, thanks for clearing it up.
Is there a, like, I guess, like, is there a reason it's not like parentheses around like the A plus B? And then
Yeah, it
on
could
end
be.
As opposed to, or, because I feel like that could get weird when you're just, like, when you've got A, the constant, plus B mod n.
I mean, what I would do is just, when I'm doing some string of things, just write out
Yeah.
onto the side, just like all this shit's here, so, yeah. Just one per, one per computation is
Yeah.
plenty. Is this okay?
So then you mod
Yes.
5, once you've already found the 3 and the 2, you mod those one more time?
That is correct,
Okay.
yes. And I just keep modding until I get down to my representations.
Oh, so it's like what we did, on Monday, where we were dividing A into B, going recursively,
Yes,
or, yeah,
kind of like that, yeah.
is it like that? Okay.
It's like, yeah, in a way, it's a recursive thing, you can
Okay.
think of it that way, yes.
Okay.
In your computer mind,
Yeah.
yes,
Okay.
recursion.
Cool.
While not in this set, reduce, Sophie.
Got it.
Okay. All right, let's have some fun. Now this is where the fun stuff starts. So let's take a look at Z mod 4. And let's do some arithmetic tables in there. Let's do a plus and let's do a times table. Z mod 4. So we're gonna have 0, 1, 2, 3, 0, 1, 2, 3. And I'm gonna put this like this, even though that 0 is gonna be very pedantic and redundant. Let's still think about it. And let me just wait until let me just make sure everybody's caught up. I know there's stuff to be written. If you want, start knocking these out, these tables. Actually, maybe that's a good idea. Why don't we just try these? And get them worked out.
Is it like 0 plus 0 mod 4?
Yeah, so like this first row and this first column, those are pretty chill. They're literally just 0 plus those things. But all your answers should come back to 0, 1, 2, or 3. Does that help clarify what I'm looking for? Yeah, okay. This is the kind of stuff I just love doing for meditative purposes. It's very soothing. Give me a grade. Cool. Good.
Multiplication says 2 and 2 is 0.
Oh, yeah, thank you. Yep, it is a 0. You were right, sir. 3, 2. Thank you. Yes. Just notice if you notice any interesting patterns in these. Are there any sorts of features just in terms of the way these tables look that strikes you, just like something worth noting? There's lots of things worth noting for sure. But are there any symmetries in the tables? What do you think? Yes, my friend.
In the first table, like if you look like diagonally, they're all,
Oh, like,
yeah. It's
Yeah.
all like the same.
so there's some pretty patterns this way, right? Those constant sums going this way. What about going this way? Is there anything interesting? What's that?
It's alternating, so it's like 0, 2, 0, 2.
Ooh,
3.
yeah, that's definitely, yes, got that, yes.
It's always a combination of 1 or 2 digits. There'll never be more than 2 values in a
True.
diagonal.
Yeah, yes. Notice how there's no repeats of any value in any row or column. In fact, every row or column here has all the digits just permuted. So each of these is just a permutation of the original rows and columns. What about if I tried to fold it across that line? Symmetric. So it's symmetric about that diagonal.
Get the reflexivity kind of idea?
So it is, yes, kind of, it's actually commutivity. That's what we're seeing here. Because so this symmetry, let's just put a few notes here. The symmetry on the diagonal is because A plus B is equal to B plus A mod n. Because normal addition is commutative, so this is commutivity. And we'll have a much fancier word for that by the end of the hour, but for right now, just notice that that sort of symmetry there is because it doesn't matter what order you do the operations. We see that same thing over here, right? See that same symmetry down the diagonal. So this is also commutative. This one kind of lacks that property over here that every digit appears in every row or column, though. So take a look at this row. It's missing a 1 and a 3. This column is missing a 1 and a 3. Didn't really need these guys. They're pretty not informative at all. I mean, in some ways, this is also the same over here, not super informative, but you never know. But over here, 0 kind of doesn't really add any information, but we got that dang 0 in the middle. And we're gonna talk about that in just a minute, because that's a little bit weird. What I wanna point out here is that 2 times 2 is 0 here. That's odd, and that's going to be a problem for us as we move forward. So just paying attention to, just note that 2 times 2 equals 0 mod 4. That's 0 right in the middle. We'll come back to that. So there's some cool things that are hard to see from these tables, but these tables are very useful to, first off, they're just fun to make. They're soothing to make, but then we can gain some information. You don't quite know how to see the information yet, but by the end of the class you will. So there are patterns arising here in these things that are examples of groups, and I'm going to define that officially in a little bit, but these are examples of groups that have a rich structure inside, and we don't have the tools or the knowledge to see it yet. But the rest of this course is looking at a group, which is essentially a collection of objects that we can combine into objects from the original set in a certain way, and there's rich structures that emerge from this. So, what am I talking about here? Well, this is all summed up in proposition 3-4 in our book, and I'm going to summarize that here. So in Z mod n, this is a summary of that. I'm not going to write out the whole dang thing. You probably won't even read the whole dang thing. So let's just try to get it out here. First one is that plus and times are commutative. We just talked about that. So order is unimportant. A plus B equals B plus A. And they are associative. And let's write out what that means, because that's actually a super important thing for us. This is more important for us than that is. So associative, first off, for addition, that means if I do A plus B and figure that out, then add C, I get the same thing as if I had added C and B first and then added A. And the same thing works for multiplication. Multiply those two, then times this equals the other two times that first one. So associativity means you can associate different pairs in a computation and still get the same answer. We're associating with parentheses. So we got that. The next thing is that A plus 0, and there, sorry, this should put equivalence there, because when we're working in the modular things, we use that triple equality. And then A plus 0 is A for all A and Z mod n. And A times 1 is equivalent to A for all A in Z mod n. So this 0 here, that 0 class, this is called the additive identity. So let's put a little note here. 0 is the additive identity. It's the thing that doesn't change a result when you add it to something. And 1, the 1 class, is the multiplicative identity. And then we also have one last property. Well, we actually have 2 more properties here. This next property is that multiplication is distributive over addition. And this is called the distributive property. You generally just call it the distributive property. But here we have these 2 different things for combining, addition and multiplication. So we say multiplication is distributive over addition. And what that means is that A times B plus C is equivalent to A times B plus A times C. So the distributive property as you like it normally. And that's mod n. Everything's mod n. And these all hold true for C mod n. Here is another one, and these are starting to get a little richer. For every A in Z mod n, and that's a kind of a fixed thing, there is minus A in Z mod n, and this is notation. This is just notation, because there are no negatives, right? It's 0, 1, 2, 3, 4, up. This is pure notation. So don't be looking for negatives, even though you could think of negatives in there. There is a negative A in Z mod n such that A plus that thing equals 0. i.e., every, and I'll put in this in common speak here, common tongue, every element has an additive inverse. So let's talk about that over here. We can see that over here in this table. What is the additive inverse of 3? What plus 3 gives me 0? 1. So I could write minus 3 is equivalent to 1. The additive inverse of 3 is 1. See how that notation works? And in fact, if you actually went to look at minus 3 in the classes, it would fall into the 1 class. These are in the same class. So what's the additive inverse of 2? Minus 2 is 2. It's its own inverse. Exactly. We pretty much got it all out here because the additive inverse of 1 is then positive 3. Whatever adds up to 4, whatever gets you to that modulo is your additive inverse. Is this making sense?
Can you
Yes.
like explain how you got the negative 3?
I absolutely can. So, if I were to say to you, I give you a 3 and then I ask you, Sophie, what's the additive inverse of 3? I put a minus here, so this is a question. What do I add to 3 to get 0?
Oh, negative 3. To get
From
to get
this set here.
Oh,
So what do I add to 3 to get a 0 out?
I guess that's the part I'm stuck at.
Okay, so here's 3. Here's the 3 row, right?
Yeah.
3 plus 0 is 3. 3 plus 1 is 0.
Oh,
So the additive inverse of 3 is 1.
I see.
You see?
Yes.
Cool. We good? So it's kind of like a notational thing, this minus sign. It's not in the same way. We have to leave behind some of our primitive notions of things as we get more abstract. And this is a good first step. This next one is very complex, and it's so complex that we're going to prove it with a beautiful, beautiful proof. So, if A is an element of Z mod n mod 0, so this is a general statement here, then there is a B in Z mod n sans 0. So this is set subtraction. This means I'm removing the 0 from the set. So it's just the 1, 2, on up to n minus 1. Just take the 0 out. There is a B in that same set. Sorry, I lost my place on my page. Such that A times B is equivalent to 1 mod n if and only if the GCD of A and N is 1. Okay, shit's getting serious. Can you say everything we've done this semester in one sentence? Pretty much right there. Sorry, I'm gonna turn on this light just up front, just for the recording's sake. Oh, sorry. I'll do that to you. I literally heard bacon frying inside the switch when I flipped it. Ah,
That's okay.
it's Regis.
To be expected.
To be expected. All right. So we're gonna prove that, and this seems pretty heavy, but let's actually talk about it for a minute. Let's look at an example so that this can make some sense. So let's say I am in, oh, here, oh shit, I'm gonna put my table back up. Let me put my table back up. And I'm gonna get rid of, this is my multiplication table, and this is Z4. You already have this, so you don't need to recopy it. 1, 2, 3, 2, 3. 2 times 2 is 4, that's mod 1.
0?
0, shit, I did that again. I made the same mistake last time. I'm like modding 3, and then 2,
Yeah.
2, and 2. No,
1.
1, thank you. Yes, 9. Okay, thank you. So what we're looking for here are multiplicative inverses. If I have, so I'm given this A here. I'm given this A. I want to find the thing that I multiply by it to give me 1. So what I'm looking for here is B equals the multiplicative inverse of A. Much more complicated than the additive inverse. So I'm looking for the thing that I multiply by a number that gives me the multiplicative identity. So i.e., A times B equals 1, which is the multiplicative identity. So I come over here, and I would actually use this notation. We would write, in the case that this holds true, that A inverse equals B. So that's literally kind of like 1 over A, but it's not 1 over A because we don't have division. So this is notation. This is the multiplicative inverse notation. So make this, because I fucked this up when I first started learning algebra. I had people laugh at me in my class because I got up and thought some things that were insane. And I'm never gonna let you think that. It was really embarrassing. I was at Purdue, I was in algebra, I was working with some people. I didn't know anything. I was completely lost all the time. And these people were like, hey, did you get number 7 on the homework? And I was like, yeah, it was pretty easy, I think. And they were like, wow, really? Show us. And I stood up and everybody laughed and they were like, good one. They thought I was joking. And I was like, yeah, I'm never speaking again in this group. So it was almost as bad as thinking that that's 1 over A. This is not 1 over A because that don't make sense in this world. We don't have division. We just have notation. This is pure notation, so don't get crazy with it. Notation. Okay, I spelled notation right. I've totally blown my confidence by remembering old trauma. So I come here and I say to myself, what is the multiplicative inverse of 3? It's 3. It equals 3 because 3 times 3 equals 1. Does that make sense?
Yeah.
What's the multiplicative inverse of 2?
Doesn't have 1.
There isn't one. So let's write this out. But 2 inverse does not exist. Now, let's look at this statement over here, because this statement is telling us that there is a multiplicative inverse if the thing you're trying to find the inverse of has a greatest common divisor of 1 with the mod of the group. So let's come over here, So we know that we have a solution to this equation essentially. Let's see, what did I write? A, B over there. Yeah, to A times X equals 1 if the GCD of A and 4 equals 1. If the thing I'm trying to find the inverse of has a greatest common divisor of 1 with the modulo of the group, then I got it. But when A equals 2, what is the GCD of 2 and 4? 2. That doesn't have an inverse. The only things that have inverses in this group are the ones that have a greatest common divisor. The only thing that divides both of them is 1. That's the biggest thing that divides both of them. So this is not equal to 1, so we expect it doesn't have an inverse, and we can look at the Cayley table. These are called Cayley tables, after some Scottish algebraist. Cayley, I guess. I think he's Scottish, who cares? That's called the Cayley table. We can see that in front of us.
I have a question then.
Yes?
Does that mean that prime numbers will always have a multiplicative identity?
Well, wow, that's all right, look at that. Holy shit.
I'll pull that one out of my back pocket.
You pulled some good shit out there. So if I had Z mod a prime, everything in there has an inverse. Because the only thing that divides P is 1.
So
and
if we
P
had like
itself.
Z mod 3,
Z mod 3, let's look
everything
at it.
would have a...
Yes, damn, that's good. You're like jumping ahead, but that's so good. So yeah,
Wow.
so let's take a
There's
look.
the day.
Yeah, let's take a look at, I would call it Sophie's theorem, but it's probably already a theorem. But,
Damn.
you know, for today, it can be that. If I took a look at Z mod 3, and I looked at the times table, 1, 2, 3, 1, 2, 3.
Wouldn't it just be 1 and 2?
Thank you. Correct. Yes. Thank you. Good. You guys are good. You're keeping me straight. So we got 1, 2. This one's pretty chill. What's 2 times 2? 4. What's that? Mod 3?
1.
Nice. So everybody's got an inverse here. I see a 1 in every row and column. Everybody's got an inverse. So the inverse of 2 is what?
2.
2. Because 2 times 2 is 1. What's 1 inverse? 1. There you go. Thanks. And now we got them all. There's only 2 damn things in there. If we throw out 0. Kayla, got any questions? Okay, cool. I was just trying to like gauge the shape of your eyes. Okay. Yeah, really nice, Sophie. I want to prove this theorem over here because the proof pulls together so much of what we've already done. And we're going to spend more time with this, I promise. I also think I did put up a new homework assignment. And I put a link to it in the book so that no one could say, where are these problems next Tuesday? Because they're due next Wednesday. So I put the damn link there for you. And the list of problems refers to the page that I linked to. We will do more problems off that page as well. We've got a lot of work to do on this stuff. So, proof of this thing here. Let me rewrite it so I can just have everything all pretty. So theorem, make it nice proof here. If A is an element of Z mod n and it's not 0, there is a B in Z mod n sans 0 such that AB is equivalent to 1 mod n if and only if GCD of A and n equals 1. So we have an if and only if statement here. We have a biconditional, just to refresh our memory on that. And I know Christian knows what that is because he was in doing just like math on his own, talking about this stuff. So biconditional. And that means the proof has two directions. We have to prove the if. So the if is actually this direction. You assume this, show this follows. And then the only if is this direction. This is necessity and sufficiency. So necessary and sufficient conditions. That's another way to say the same damn thing. Proof. Let's see, where did I start? So we're gonna start, we're gonna do the if first. So first, this direction. We're going to assume that, well, we're assuming all the basics, that A is not 0, it's in Z mod N, and we're going to assume that the GCD of A and N is equal to 1. What cool results do I know about the GCD? It was like a really surprising one. That
So 1 is a linear combination of A and N.
beautiful. So this means there exists an S and a T that are integers such that S times A plus, actually, let's actually say there's a B and a T such that B times A plus T times N equals 1. Remember, we can get that linear combination. This shit is so important. That result is going to save you so many times. It's really potent, and you're gonna see that right here. So simply because GCD of A and N is 1, I can write this linear combination, and I've knowingly picked B instead of S because I know that I kind of want a B in my final thing. All right, so this implies that B times A equals 1 minus T to the N. Just subtracted T times N from both sides. Let's take modulo N of each side. So now the left side, to take that, I'm just gonna write this. And let's just go ahead and write this. Let's actually do a step in between. And then 1 minus T sub N mod N. What is this right side simplified to?
1 minus T?
What's that? Careful, it's not, the T is times the N, so be careful.
So then it's just.
So this is a multiple. It's not, yeah, this goes to 0, right?
And then
So it's
the
just
other thing goes
1?
at N.
This just goes to 1. Right, so think about how we do subtraction. This is 1 mod N. And if N's bigger than 1, it's just gonna be 1, and we hope that N is bigger than 1, otherwise, what are we doing with our lives? Minus or plus negative T times N mod N. And what is this? It's a multiple of N. So what's this equivalent to? 0. So the right-hand side, when I mod it, because I just got 1 plus a multiple of N, this essentially goes away. And I'm just left with B times A mod N equals 1. Mod N. And we could put the mod N out here and just have one of them for the whole thing. This actually tells me how to solve the problem as well. In some ways, it's like I just gotta get this linear combination and then do all this stuff, and I've got my B right here. Although finding this can be a real pain in the ass if you've done any of the homework. Well, you don't have any yet, so you haven't. You'll find out. Any questions on that direction? Because I kind of love this proof. I love that this thing is kicking in there. I wanna do the converse. And we're gonna kind of get at this guy. So we're gonna work backwards. We're gonna come up with something like this, and that's gonna give us that, just so you can see where we're headed. But let's do the other direction formally.
So because we found that b times a mod n equals 1, that's what we needed to show.
That is what we needed, yes. So that's this part right here. So actually, now, let me actually formalize that just a little bit more, Sophie. Because here I have b times a, so in other words, a times b, because it's all commutative, is equivalent to 1 mod n. Just to make it really clear that I hit this result over here.
Mhm.
Does that sound better?
Yeah.
Okay, cool. Thank you for saying that, because that does make it better. Then, conversely, so this is the other direction. This is the only if direction. So that means I'm going to assume this and show that this must result from it. It's actually pretty straightforward. I don't think I even need my notes. So we're going to assume that AB is equivalent to 1 mod n, and we're just gonna write out what that means. What that means is that A times B is equal to 1 plus some multiple of n. Let me stop, and please make sure that you do see why I'm saying that. Yes, need nods from I've seen some nods. I got nods. You go here. You three are good. You stop nodding. You stop nodding. You good? Camila? Kayla? Not yet? Huh?
No.
Was that a nod? That is like a super high frequency nod. It's like I couldn't even see it. It was almost so. Sophie, we good?
Yeah.
Okay, awesome. All right. So I got this. Where do I go next? Tell me where to go. I want to show that the GCD of A and N is 1. Cormac, where do I go?
I would subtract a n.
I like it. So we're going to take AB, and I'll even do it like this, right? Just to be super saucy about it. Where do I go next, Cormac? Because you got the move.
Isn't that kind of the definition of GCD?
Kind of is, it's that result, right? Because I wrote A and N as an integer linear combination that adds up to 1, this is the GCD. So, therefore, 1 is equal to the GCD of A and N. Because we wrote it as a linear combination, an integral linear combination. I don't know what we called that result, but yes, sir. Yeah.
Just for like fun, could you also say 1 is the greatest common denominator of b and n, or b and negative k?
So wait, say that again?
Could you also say 1, like, it doesn't matter to the problem, but is 1 also the greatest common denominator of like b and n, b and negative k?
Well, we don't have fractions. You're saying denominators.
Or greatest common divisor.
Oh, okay, gotcha. So say it again now.
Greatest common divisor of like b and negative k and b and n.
Oh,
Just 'cause-
yes. Yeah, so same thing with B. Yeah, exactly. I think that's what you're saying, right? Yeah, so you can make the statement about B or A or K. Yeah, yes. We good? We just proved it. Cool. So, that means, let's put up Sophie's theorem, because I'm just gonna do it. I don't think we hit it for a while, but let's just freaking put it up. And actually, let's get a couple definitions. I didn't even see it. I didn't plan on this, but it's just happened because of Sophie's thing. And it's a good thing, Sophie. I'm not casting aspersions.
Yeah.
Yeah. So we have like a little theorem. If P is prime, then every element in Z mod P, but we gotta take out the zero. The zero blows everything, because 0 times anything is 0. No way you're getting 1. Every element in Z mod P has a multiplicative inverse. Because everything inside here, so Z mod P is 1, 2, on up to P minus 1. If P is prime, the only thing that divides P is this 1. So let's just make a little note here. Because the GCD of a prime and any number less than the prime is 1. Because the only thing that divides the prime is 1 and itself, and we can't even get to itself. Because itself is 0. It's in the 0 class. Cool, that's a great theorem. Let's get a definition out here. You'll need this for your homework. I was gonna make you read it and find it in the book, but let's just talk about it since we're here. So there's a companion to Z mod n, and it's called the unitary group, and it's written U sub n. So it's equal to the collection of all invertible elements of Z mod n. So we basically insist, we're gonna go to Z mod n, we're gonna take out everything that doesn't have a multiplicative inverse. So for example then, U3, we already kind of did this. This is just 1 and 2. So I'm gonna take out everything that's that's not relatively prime to n. So equals, let's see here, we can do another version of this, equals the set of all classes K in Z mod n such that GCD of K and n is 1. Kind of just referring back to this result, right up the previous result that we had. So U3 is these guys. U4, what's U4? Because we have that Cayley table, we could like pull it out. 1 and 3. 2 didn't have the inverse. Oh,
Right, yeah.
does that make sense?
Yeah.
So this was just 1 and 3. While we're here, let's just look at something kind of interesting. So U3, since 3 is prime, I don't have to take anybody out because no one can be relatively prime to 3. Or I mean, no one cannot be relatively prime to 3. So this is my U3 table with multiplication. We've got 1, 2, 1, 2, 1, 2, 1, 2. 2 times 2 is 1. But let's look at this one. And we're about to see something very interesting that is kind of at the heart of algebra. So again, we do times. Can you do the times table, please? Just so you're not just watching me. Notice how they're kind of the same. And it's not, the numbers are different, right? There's one's got a 2 in it, one's got a 3 in it. But there is a rhythm here that is identical. In fact, if I had a little table and I had a 1 and an A and I didn't know what A was, and I had a 1 and an A and I knew this, this rhythm occurs in both those places. So what I want to just point out here, we'll get a fancier word for this called isomorphic a little later on, but they have the same rhythm. How do you say, God, I can never spell rhythm.
Are you asking for isomorphic or?
I'm asking how to spell the word.
R-H-Y-T-H-M.
R-H-Y,
There's an
that's
H
it. Okay,
before it,
thank
which is
you.
Really, really wrong.
Wait.
but
Really?
Yeah,
Rhythm.
it's nasty.
Oh, it's like that. Okay, got it.
Yeah.
Okay, thanks.
Yeah,
Thank you.
it shouldn't be like that.
That's all right. I present my vulnerability and ignorance. I've got rhythm, I just can't spell it. All right. So what is, let's just write this out. What is U6? What does its table look like? Yeah, there's one more though. Yeah. So tell me your thought process.
I'm just like trying to picture, I'm trying to make the table with my.
Oh, okay. But maybe just find out what's in the table first. So like, what are relatively primed is 6 between 1 and 6? You're just missing one. Surely 1, right?
3.
Are 3 and 6 relatively?
Oh, they're not
They are
relative.
not. So
Sorry.
2 isn't in there, 3 isn't in. What about 4?
No, because that's got 2 in
They
it.
share 2. So 5 works. What?
Are all tables only ever gonna be
No.
2 by 2 or?
No, we're just enjoying this for the time
Okay.
being. No. But the rhythm is the same, right? Rhythms, there's the same rhythm. Again, let's prove to ourselves that this maybe isn't always the way the tables look. Can we do U8? And the U stands for unit. Does that make sense? Yeah. This one's a little more interesting, for sure. And then see if you can get, do the table, because the tables are fun. Cool? Yeah. Nice. Notice here in this Cayley table, each element occurs exactly once in each row and each column. So I knew that was gonna happen and totally cheesed out on some of them because I was like, what am I missing here? Oh, that's the last one. So you can do that if you know you have a certain structure. Is there any questions I can answer on that example? We feel good. This is like, you hope your homework's this, right? It's not. Your homework's more like this. Some of your homework's chill. But what I'm saying, when I say that every row has exactly one occurrence of each element, and same with every column, I know that this is what's called a group structure. And so that's what we're gonna talk about next. So definition, this is like, this is literally the rest of the semester. This guy right here. So I better get it right. G is a set. Your favorite set, whatever set you want. We're gonna let, and your book uses this open circle, so I'm just gonna use that. Looks like a composition symbol for functions, which is not a bad thing to use for this. And this is a binary operation, and I'll explain that, on G. So in other words, that's a function, that's a mapping. So this circle maps from G crossed with itself back into G. This circle takes a pair of things from that cross product, from that Cartesian product, and spits out a single thing that we denote as A times B, or A composed with B, but I'll probably call it times. So when we say times, we don't always mean multiplication like you're used to. It's just the group operation. So you might even just read this as AB, but probably you'll say A times B, and most people will when we say that. So this is similar to over here, right? This is our binary operation. It was multiplication. When we had the integers mod n, the addition was our binary operation. You added two things and got something back. So this looks very abstract, but you've seen it. So, like this, then parenthesis G and this binary operation, so we're pairing them together. That's not a Cartesian pair, it's just a pairing to show that they are combined and mixing together, is a group, structure, if we have the following properties. And the first one is associativity. So in other words, if I take A times B and do that first and then do C, I get A times if I first do B and C and then multiply them. So I can move parentheses. I can group things and do things in different orders, as not in different orders, but in different groupings. Notice the order is identical here. I didn't change the order at all. For each A in G, there is an inverse. An element A inverse in G. And again, this is notation. That you just read that as A inverse. Such that A times A inverse equals A inverse times A. And because I wrote it really small, I'm gonna put this here and then I'm gonna go back and define it right in this little space right here. Equals E. Let's put a little note here. The identity element. What do I mean by the identity element? Well, shit, you gotta squeeze it in here. There is an element, E in G, that acts like an identity element, so that AE is AEA. When you compose it with any element of the group, you just get that guy back for all A and G. So let you get caught up in writing. And honestly, that's it. Just these three properties, which is not much. And that's honestly what makes this all so hard, is that you don't have the things you're used to. You have many less operations you can make. So we have a group. If I have associativity, there's an identity element, and everybody has an inverse. That's it. And you can't talk about inverses until you know what the identity is. So here's a group. This is associative because integers are associative. Integer multiplication is associative. So this guy here is a group. And I go through and I check associative. Yep. Because integers, integer multiplication is associative. So you don't have to go back and prove everything. You know some things. You know things. Right? We had this discussion a little earlier. Like there's certain things we know that we can just fall back on. And you know that you can do integer operations in any order. So you're good to go on that. What is my identity here? What is the element that when I compose it with anything else, I get that thing back? 1. That's why those rows and columns are the same as the outside ones. So here, it's just 1, the identity element. 1 times anything is that thing. And then, does everything have an inverse? And how do I know that? Does, yes. How do I know it? Everybody's got a 1 in their row and column, right? Everybody, I can find the inverse of everybody. So everybody's inverse is actually like just themselves in this guy. Everybody's their own inverse. But there's a 1 in every row and column here. So I see that. So, I'm just inverses. Yep. That's what I said, not what I wrote. The yep is a little insufficient. All right, so we've got a couple minutes and I want to do one more example. There are some things that you're gonna have to kind of, please, over the weekend, please look at these problems. Over the weekend. This stuff is starting to get heavy enough that it's not like Tuesday night stuff anymore. Seriously, you gotta it's gonna take some like rearranging things in your brain. And so give yourself the chance to have that time to process this all. But I got one last example in the last 3 minutes. Shit. And I might have to ask you to go read it a little bit. Shit. How about, here's the example. Read it in the book.
Awesome.
So, also, for Monday, read the example. This is the thing I was gonna make copies of, but we'll start here on Monday, of the group of symmetries. This is pretty and cool. Symmetries of an equilateral triangle. Check that out. So what we do is we look at all the different ways a triangle can be flipped back onto itself or rotated back onto itself. And in some ways, this whole class, abstract algebra, is really just abstracted symmetry. That would be another name for this class that would be completely legit. We're just thinking of symmetry in a way you've never thought of it before. So that's it. Thanks, friends. I do like these Monday, Wednesday classes. They are pretty sweet. Right?
It's
They're
so
like,
nice
all
not
right.
having a Friday for once.
I know, and I like having the whole time because you give people time to digest.
I do too. I like 75 minutes. Like 50 never feels like enough.
By the time you get settled in and go over everything.
Exactly. I agree. Yeah. I think more people, I used to be the only one who did these in the math department, but I think more people like Cybert, I think, have started doing them and. Anybody-
Differential equations is like this now, so.
It's also really nice to not have to be here on Fridays.
That's honestly the best part.
I am still
STEM
here.
major on this campus is the worst.
What it being
Being a STEM major on this campus.
Oh,
because
so
they were like,
awful.
let's do only Friday classes for STEM majors and freshmen.
Oh, yeah, and the freshman class is the worst.
Yeah,
This is
I
the
know.
only semester I've had a Friday.
me too.
Same.
This is the first time.
Yeah, and it's my best one.
Well, I'm glad you get to go out with a bang.
Abraham, did you see that?
Oh, you're doing your teaching in the spring? Okay, cool.
Died.
Cool, cool, cool.
He died. He did.
You did that.
Charlie Kirk died.
Yeah. Really?
Yeah.
I'm gonna go watch that South Park.
Oh yeah, there is going to be a South Park, you know. That's a good point. That's a really good point.
There's a new one tonight, right?
Also, I wonder what's going on in the high school.
I think
because
it's
apparently
now.
it's still going on.
It's
Oh,
still
no.
going on?
It's supposedly there's still an active shooter at that high school. So,
Where's this Evergreen? Where's
Evergreen High School?
yeah.
It's north, I think.
Oh, it's not in Westminster, is it?
It's in Evergreen.
Oh. Oh, it's in Evergreen.
It's the Evergreen High
Oh,
School.
got it, okay.
Yeah. Yikes. A
Yikes.
bad day
Oh
to
my
be a US
God.
citizen.
That's horrible.
That's very scary. That's
That I
very
have
scary.
great sorrow for.
Me too.
I don't, not forget.
Thank you.
Thank
Doc.
you, thanks for the news too. Bye.
Are groups always defined for like modular arithmetic?
No.
Are vector spaces groups then? Cause they like.
Vector space has group structure in it, but it's actually, of fields, it's more of a field structure.
Okay. Huh.
So those are just richer, so you've got groups, and then the next structure, if you have like two operations, like times and plus,
Because I was gonna ask if like you could define a single group for multiple operations.
so it becomes what's called a ring then.
Oh.
So you move up, we don't even talk about that, because this ends up
We
being
don't
like
get
a
that.
lifetime of study, just with these simple, this three things right here, like it's crazy what's gonna happen. But yeah, vector spaces are so much richer that you can like do all the things you wish you could,
Yeah.
but in groups, so like what I did in my thing was, I think I did something like assumed I could just divide cancel A in something, and I couldn't. So like just the basic things, here we kinda could, but,
Yeah.
oh no, it's like this. So if I have like AB equals CA,
Oh,
no,
because commutativity is.
we don't have commutativity, yeah. And so I was just like, oh, blah, 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 and they were like, that's funny, what a funny fellow, and I was like, I'm dying inside.
Yeah.
Yeah.
Dead serious.
Yeah, I think I stopped going to that study group. It's like, well, I'm just gonna
Understandable.
fail on my own and not be humiliated.
Yeah.
Alright, I will, get you some problems.
Yeah, let me know. I'm
Will.
happy to start whenever.
Okay. I got them for you, alright, thanks.
I'll see you later.
See ya.
I just wanna check my understanding. So if we have like Z mod 6, this is like the first, not that table, but the.
Correct.
Right?
Yeah.
So then this only has 1 and 5 in it because every other column has a 0.
Yes.
Okay.
Yeah,
Just wanted to make sure.
exactly.
That's what I was saying when I was like.
And they don't have a one in them either.
Oh, okay.
That's kind of the point I was mostly making, that there's no
Oh.
multiplicative inverse for 2 or 4
2 and 3, okay.
and 3, I guess either. Yeah, like,
Okay.
what do you multiply by 3 to get 1? You know?
Okay.
Yeah.
That makes sense.
Yeah,
Thank you.
you're welcome. Things are starting to get really interesting.
I'm having a fun time though.
Are you enjoying
Yeah,
it?
I am.
Nice.
I think I'm understanding everything. So.
That's you. You're doing so good. You're doing so good.
I think it was the first week was kind of scary because I just didn't understand the notation of
Sure.
everything, but now I understand the notation. So I'm like, okay.
Yeah, you're amazing. Wait, are you not graduating this semester, are you?
No, next semester.
Oh, okay.
Yeah.
Are you doing the math minor?
Yeah.
How much more do you need? Is this it?
Oh, wait, let's shut this show down.
No, I'm taking two math, courses